Great. So first, I should thank Kentaro for inviting me, and also, during this special stage in China, we can't travel, so he suggested that I could give a remote talk. It turns out my job actually becomes, quite related to remote talk. So I'll just show you one slide here. So this is what's happening in Tsingha University, I think, yesterday. So that's the first day of the semester, and I'm not in the university yet. I'm still in the Hainan Island, because we were spending a holiday here, and we were suggested not to travel too much. So this is what our university is trying to do, is trying to make sure, each of the professors is giving his lecture remotely, just like what we are doing now, to give the classes to all the students. So all the courses, although the students are not returning to the campus, we have to keep on giving courses through the internet services. So this is what I was doing yesterday, giving a course on the internet. If you can recognize some of the Chinese characters, that's quite related to what I will be talking about today, deep learning for remote sensing. Okay, so for my research work, as Kentaro has mentioned, we have a research group back in Tsinghua, and also we are doing a lot of application work based on the Sunway Taihu Light supercomputer. So this is a figure I got, I think, from the website of the very famous supercomputer in Japan, the Earth Simulator. And I like this figure very much because it very clearly shows what the scientists want to use the supercomputer for, right? What we want to do is to create a digital Earth so that we can simulate different processes on the Earth. We can analyze all these different data that we get from different sources, from satellites to the stations all over the world. And we will try to understand what is the mechanism for all these different changes, and we build models to make predictions and to help the society to mitigate different kinds of changes or disasters. So as we can see, the two major roles that we use the supercomputer for, one is to do the simulation. So in that part, we try to provide, say, highly efficient and highly scalable simulation applications. So before actually going into the major part of the talk about the AI methods for big data analysis, I will just mention a few examples here that is happening on the Sunway Taihu Light supercomputer. So this one is actually the very first project we started on Sunway Taihu Light. It started before the machine was ready. I think we started the team during the summer of 2015. So when the hardware team is building the system, we were trying to port CESM, the Earth system model, onto the system, kind of to make sure that this supercomputer can provide good support for climate scientists. So in that summer, we tried to port the entire code, but I think till now we still have a team working on this, trying to redesign and re-optimize all these different modules for the very different CPU architecture of Sunway Taihu Light, and to make it efficient on this supercomputer. Another example is for earthquake simulation platforms. So this is a work we started in the year of 2017. So we were collaborating with scientists in China and also from US. We would try to port the earthquake simulation codes, both for the source, the dynamic rupture source generator, and for the more time-consuming propagation of the ground motion onto the Sunway Taihu-like supercomputer. Now the work is now more so. The very first platform was targeting the Tangshan earthquake, which is more like a plain region in China. And now we are moving the focus to the Sichuan and Yunnan provinces, where the most of the earthquakes are happening in China. And if you look at the figure, you can see that the geographic pattern is very different. There's a lot of mountains. It's actually the region where the Tibet Plateau gradually meets the plain area in China. So that's where there's a lot of faults and earthquakes happening along the area. So to support the complex surface topography, we move from the original AWP code from San Diego Earthquake Center to another code developed by scientists from the Southern University of Science and Technology in China, led by Professor Xiaofei Chen. So using the curvilinear transformations, we try to keep the irregular grid in the compute, but we can use it to describe very complex surface topography. So this one is a recent result we have made the animation for. Is for the Wenchuan earthquake, and you can see more clearly from this video that the region we want to simulate is very complex, and especially a lot of the activities are happening along the region between the hills and the basin. So that's where we want to make it more accurate. Okay, so that's just a few examples about the sort of the simulation tools on supercomputer. And nowadays we see more and more demands from the data, from the side of the data analysis side. So I think there's actually more and more groups within the center and also within my department in Tsinghua University. They are putting more research resources into developing intelligent data mining methods for the analysis of big scientific data. I guess many of you would be quite familiar with this figure from one of the articles published in Science. I think quite a few years ago. It was predicting that we would have over 100 petabytes of data around the year of 2020. I think we already have more than that for climate change studies. So this is a huge challenge, but also a huge opportunity. And if you look at the bars, actually half of the data, simulation data provided by different simulation models, just the examples we have shown just before. And the other half of them is actually coming from the satellites, the remote sensing data. So that's actually quite a big focus of what we want to use the supercomputing resources to analyze. So if you look at the remote sensing data, it's also growing quite fast. If you look at the resolution, maybe 10 years ago or say 8 years ago, when I first joined my department, most of my colleagues are still dealing with, 30-meter resolution Landsat satellite datasets. And nowadays, all of them are moving towards, 3-meter or 7-meter resolution, high resolution satellite images, and even UAV images, which can have even higher resolution. And this one is kind of a summary slide of quite a few different remote sensing research groups in my university. that they use the remote sensing images to deal with different kind of scientific problems that they want to solve. If we look from the left to the right, so the first one, the land cover mapping, mainly led by Professor Gong Peng in my department. So they are trying to use especially the free public remote sensing data like Landsat or Sentinel, trying to produce global level land cover mapping data sets that other scientists could use. So basically automatically determine different regions on the Earth to be a forest, a desert, a lake, a desert, a lake, or a human building. The other scientists, they use the same kind of remote sensing data to investigate problems like ecology protection zones, where you should put it, and whether this zone is working effectively in the past few years or in the past decade, something like that. And also migration of birds. Now this is of course more complicated. You can't see them from the remote sensing images, so you have to attach some GPS devices to different kinds of birds that you want to study. So there's a female professor in our department who is doing work, very interesting work about this. And now city is of course a key issue that people are looking right now. So how the city is developing over the years and how the land use is changing over the years, whether it's going in the right direction, whether it's sustainable, whether it's good enough to provide support for public health, for good transportation within the city, and these are becoming very important topics that people want to study. Greenland, that's another thing, and of course water like the lakes. A few years ago, people are very concerned because some of the major lakes are shrinking significantly in China. So using remote sensing, you can very clearly get a good picture, and also you have history, right? You can look back in the years to find out how they actually change over time, and also the sea level. You can see, of course, that's remote sensing images is probably the best way for you to look at those problems. Very interesting results from one of our colleagues' recent paper. It seems that the horizon of the land, the region of the land is actually expanding these years. But if you look at the detailed results, it's mainly because humans are still trying to expand in the land. They convert some of the sea area into buildings. So basically, we see a lot of potential in these different kinds of remote sensing data. In terms of resolution, is much higher than the current models. Talk about weather or climate model is the good ones. The best ones are probably at 1 kilometer resolution, but these ones are already, the remote sensing data are already at the level of tens of meters or a few meters or within meters. So that's much more information you can see from these images, and you can even study a specific kind of birds or trees. For trees, you can for sure recognize different kinds of trees in high resolution images. So I borrow this example from deep learning courses. If you look at the recent research activities in deep learning, you see these three major activities that people are trying to do. So the first thing is, of course, to do the image classification. You look at the image, you can the computer can tell you whether it's a cat or a dog. And then at the second level, you can move a little bit forward and trying to detect where the cat is. Now, if you move another level further, you can actually analyze the entire picture and trying to understand all the different parts, right? Each pixel you can actually you can put it into one of these different categories. You can basically from a human being's perspective, we can understand the image. Now that's three different things are very similar of what people are trying to do with the remote sensing data, right? The first thing, as we have mentioned, to classify the land cover, as I said, for the project to produce global level land cover map. That's basically you feed the data, you feed the images, and the computer trying to tell you what kind of a category. Is it a farmland, a forest, or just artificial buildings? Now the second level, now with the improvement of resolution, you can do more things. You can actually try to detect trees from the images, trying to count the trees, how many trees you can see in this region, and you can even try to measure the size of the tree. Is it like for oil palm trees, for the oil palm plantations, you can actually trying to find out whether the tree is in the right status, or you actually need to send someone to take care of the tree. So now, of course, if you move into the city, now people want to understand the city. So if you look at the very high resolution data of the image, people are now trying to really understand the different images, trying to locate the buildings, the cars, the roads, all these different elements that actually form the city. So this actually corresponds to the three different levels I've mentioned in the deep learning world. But of course, when you jump from the image side, from the remote sensing side, you see a lot of challenges. Now, the first one is, of course, about the data. Now, it takes, maybe around 10 years to build up something like ImageNet to enable all this exciting research related to image processing. For remote sensing, I think the community is trying to form something similar, but currently, for different kind of problems, still scientists need to label the data first, and then they can try to use the deep learning technologies. And of course, there are also some other issues, but currently, from my perspective, I think how to resolve the problem of labeled data. If you can find out some methods to resolve those things, that would help the current status quite a bit. So I would just show a few examples of the research that so some are done by my colleagues in Tsingha University, and some others are done by my colleagues in the Supercomputing Center. So the first one is about more accurate land cover map. So this is, I think, a very good starting point of the project. As I mentioned, Professor Gong from my department, so his group provided the first 30-meter resolution global land cover map. It also provides, by using the supercomputing resources, we don't have the subway type light yet by then. So it's mainly based on the supercomputer. Tsingha University's own supercomputer is a Intel machine with roughly 100 teraflops computing performance. With that, we can actually process the data from the entire Earth in just one day to produce this cover map. But if you look at the accuracy, it's not very high. Okay, it's mainly based on the traditional machine learning methods like random forest or support vector machine, and the accuracy is roughly 63%. So a starting point that I started to collaborate with Professor Gong, and we try to look at the potential of the deep learning methods. So the starting point is just a direct application of the stacked autoencoder into the Landsat data. And if you look at this, for this is for the region in China, it can only slightly increase the accuracy just by 1 to 2%. Now that does not sound very exciting, right? But it's still quite some valuable improvement as a starting point. So to follow that work, then we try to look at the problem. If you look at the 30-meter resolution Landsat data, you have to be an experienced remote sensing expert to actually, to read the image and to trying to determine the region to be a farmland or a forest or a building. So it actually, for normal human beings, if you just look with your eyes, you don't see a lot of pattern. So we were thinking maybe we should, try to add some more high resolution elements into the workflow. So the first thing that we try is to integrate some high resolution Google Earth image. So for the same sport on the Earth, we also utilize the traditional methods to look at the spectrum features. Okay, the Landsat data, I think it includes 7 different bands, so it provides a wide spectrum features. And then we for the same sport, we try to locate the high resolution image from the Google Earth, and we use the deep learning networks trying to extract the image patterns, the texture patterns. And then we combine these two things to produce better results. So this one shows the spectrum reflectance curve of different kinds of categories that we want to classify. And you can see that the spectrum curves, they can actually, there's a lot of difference in some of the different kinds. But for certain kinds, the curves are very similar. And this is where the texture features can actually help. So for that part, of course, we have to. So for 1 point of the 30-meter resolution, we have a 128 by 128 pixel image to correspond to that. So that's roughly. Now the other thing is actually for Google Earth images, they have they is a unified set of images from many different sources. So they have different resolutions, but roughly. This kind of a pixel would correspond to somewhere around 40 to 50 meter square. So we built a network to basically extract some of the patterns from here, and by combining these two, we produce the final result of the land cover map. So again, if you look at the accuracy, so the first blue box is actually we apply the method by only using 30-meter resolution image. You can see the improvement is only marginal. But if we actually integrate some of the high resolution images, you can see a very big jump of the accuracy. And here are some detailed results. You can see that especially for the buildings and forests, for some of the detailed regions, we can get a much better results for the land cover classification. Okay, so that's for the 30-meter. And last year, our department is moving the resolution from 30-meter to 10-meter using the Sentinel satellite images. And you can see that this is already providing global land cover map services for other scientists. And what we are currently trying to do is actually moving, again, further from 10-meter to 3-meter. And in this one, we are trying to explore some even exciting ideas. For example, we want to minimize the efforts for people to actually label the datasets. So instead of, for 30-meter and 10-meter cases, we have to, hire, specialized companies, because usually you need to do some training to really, to read the remote sensing images, especially for high resolution, for not so high resolution datasets. So in this one, we want to minimize this part. We actually feed the 10-meter results into the network as the inputs. We know it's not the perfect training data. We know there are noises in the data, but we try to fit that as the input. And of course, we have to integrate some of the new methods that people are proposing, trying to to deal with noisy data. And then we use that to train the network and to produce our 3-meter resolution land cover map. So now, of course, this one is still at the preliminary stage, but from the early stage results, we can see that for the regions in China, even though we are only using the output of 10 meter as the training input, we can, but through this training process, we can actually improve the accuracy by another 4 to 6%. That's actually quite exciting results we are seeing. So this is just a sample result. It's a land cover map we have generated for the city of Changsha. So you can see for 3 meter, you can already see a lot of the details of the city, like the roads are more or less already there. Okay, the second example I want to talk a little bit here is about the detection of oil palm trees. Also, there are different stages that we want to solve the problem here. The first one is, of course, we want to map the oil palm trees. We want to, at a course level, we want to decide which part of the region is the oil palm tree plantations. And then within these regions, we can then try to detect each of the single oil palm trees. As we said, we want to count how many trees we have here. And then we can do if we have UAV images with very high resolution, we can even measure the size. We try to detect some of the trees that are not in the normal status.
3 minutes.
So here, just some examples, for different regions we try to now. Of course, in this one, as a early start project, still we have to generate our own data sets first. We have to label them, we have to feed them into the network and then train them. Okay, so this is an example for doing the oil palm plantation extraction. As I said, trying to determine which part of the land is the oil palm trees plantations. And for CNN-based methods, what we are currently proposing to our collaborators is actually a multi-level CNN training status. So we have 2 different levels of CNN networks. The first one is trying to classify the land cover, trying to tell this part is oil palm trees or other kinds of trees. And then in the second stage, we use the CNN network to actually detect and count all these different single trees. And the current work is also quite focused on the data sets. We're trying to see if we can actually, again, to extend the research without extending the efforts on labeling the data. We want to see if the training of one source domain can actually be transferred to another target domain or to multiple target domains using the different transfer learning methods. So very quickly about the third example about the urban land use map. This work started, I think, just maybe 1 or 2 years ago. We started to look at the cities. And one thing we had in mind is that there are already many different other data sets that people have already built for cities. So the first thing is how you can actually fuse these different data sets to look at the same problems. In this example, we're trying to combine the multi-spectrum satellite images with the public GIS map datasets to trying to extract all these buildings in the city. Okay, so there are some initial results. I think currently we still have quite some region to improve on the method and to make it really valuable for city purposes. Okay, so this is I think the last slide of my talk. We are recently starting a collaboration project with the city of Xi'an. So Tsingha University, the National Supercomputing Center in Wuxi, and the GIS Center in Xi'an. We are trying to collaborate together, trying to see if we can actually contribute to what we call in China is city brain. I think you probably have similar projects in Japan, trying to integrate some of the recent IT technologies to city management. So the remote sensing images and UAV images can actually play a great role in this, trying to sort of detect the change of the city and to understand. We are very interested in this collaboration with the JS Center in Xi'an because they actually have quite a long time history of data sets they have preserved for the city. So we can actually try to look at how the city is changing over the years, trying to understand the mechanism behind the change, trying to model the change, and trying to provide support to help the city government who is making plans for the city. Okay, so with that, I should end my talk, and thanks for your attention.